Hey everybody, Brian from SEI here. In this presentation, we're going to be going through a sizing and design example for a residential scale system. We'll talk about some of the parameters and considerations to get started. We'll go through configuring the array in terms of the number of modules and how it is going to be wired. We'll talk about the electronic power converters we're going to use, look at the AC interconnection, go through our conductor sizing and overcurrent protection device sizing calculations, as well as voltage drop, and look at grounding for the system as well. Before we get into specifics, let's talk about some of the general criteria for sizing residential systems. One of the big ones is site energy use. How much energy is being used by the home? And this is going to vary considerably based on what the loads are, the numbers of occupants, the location of the house. But what is also going to vary is how energy is exchanged with the utility grid. Is it a traditional net metering where you get a credit for excess production equal to the retail rate of energy? Or is it under some other type of agreement where if you produce more than you consume, that excess production is valued at a wholesale or less than retail rate? And maybe that's done annually, where it's trued up if you have a surplus, or maybe it's on a monthly basis. All that kind of stuff differs. You really got to know the details, because once you go beyond a certain size of system, the value of the energy you produce may go down dramatically. And that necessarily means that the economics of the system will go down as the size gets larger. Now, that may not be a concern. Maybe you want to make a lot, but you got to be aware of that. That means knowing what the interconnection requirements and the rate structures are for the utility you're interconnecting with. That, of course, will also tie into any other specific utility requirements. These may be things like limitations on interconnection size, limitations on generation relative to demand over specific intervals, whatever those are. Again, you've got to know the rules, and often those will be something that will guide system design. Of course, we want to pay attention to the equipment at the building. Right? What is the service entrance? What's the voltage? Typical for most residences in the US, 120/240 split phase. You might see some three-phase houses out there, especially larger ones. And of course, we need to know the ratings of the equipment. The bus bar, the main overcurrent protection device, potentially the service conductors, and the transformer if we're connecting on the supply side for larger systems. As I said, the equipment that's there is going to have a big impact on how we interconnect, as is the size of the system. And this example will kind of give us a good look at that as we work through it. Available space. Here's a big one, right? How much roof space do you have? My experience, the bigger the house, often the fancier and crazier the roof layout, and there's more stuff up there, and there's dormers and all kinds of hips and valleys, and all of a sudden, there's not that much usable space. We also have setback requirements for emergency responder access that may be enforced, best practices for being able to access equipment on roofs, whether it's part of the PV system or other equipment. So you really got to be careful and make sure that you're looking at available space, not just the dimensions of a particular roof. Mounting method is going to play a big role as well. We'll talk about some specifics here in a little bit in regards to that. And then, of course, a big one, we put it last, but budget. This probably should have been number one on the list. What's feasible? How can it be financed? What are the economic impacts of the system? That kind of analysis is not really what we're getting into in this course, but those are big considerations for nearly all projects. Let's set the stage for the rest of the sizing that we'll be doing throughout this presentation. Here's the backdrop for the system we'll be sizing. Going to be located in Austin, Texas. We've got our ASHRAE high and low temperature data on the slide there for you. Maximum temperature 37 degrees Celsius, minimum temperature -7 degrees Celsius. We are targeting a system of about 11,000 watts of PV. So that's our DC STC, standard test condition wattage of the array, 11,000 watts. That's going to be based on the roof space, the energy usage, the budget. That's not the focus of the lesson here. Let's just start with this number, and that we're going to be targeting 11 kW. As is typical for a lot of houses out there in the US, split phase 120/240, service voltage, 200 amp main breaker, 200 amp bus bar rating, and that's a lot of what's out there. Some are bigger, some are smaller, but you'll see a lot of these. Other considerations, it's going to be going on the roof, often the most economical and often the best solar window when you get elevated up on the roof. And of course, we have to realize that for 1 and 2 family dwellings, 600 volt DC limit per the National Electrical Code. As far as the module, this is a real module. We don't have the brand here. You can look at the spec sheet. Kind of unimportant. What matters to me for this lesson is the specs of the module. And that's what we're going to be worried about and basing our sizing on. Of course, brand and cost and all that stuff matter. 345 watt module, you can see the voltage and current characteristics there, as well as the temperature coefficients, 20 amp maximum series fuse size. If we're targeting an 11 kilowatt array, 11,000 watts, divided by our 345 watt nameplate rating of our module, we're looking somewhere around 32 of them. So that's what we're going to be shooting for. We said we had space for this already. We'll see. We'll take a look at the layout here. Presumably they have the budget. We said that was good to go. So about 32 of these modules to make our array. Next, we'll look at the roof layout. I'll catch you there soon. Thanks.